Hello and welcome to this Aurox conference on microscopy. My name's Lee Rees, I'm the CEO of Aurox, and I'm just going to give a very brief introduction to the conference and to our company Aurox. Literally will be very brief. So, about 3 weeks ago, basically because of the cancellation of the FON 2020 meeting in Osaka and the prospect at that point in time of further conferences and meetings being cancelled, we thought that it might be a good idea to try and run an online conference, probably for a small number of people, which it turned into quite a large number of people in the end. So this was an idea born of that about 3 weeks ago, and I have to say we've never attempted something quite on this scale before. And indeed, the platform that we're using here today, we've only been using for the last 2 weeks, so it's all very new to us. That is to say, if we stumble, please bear with us because we're doing our best. Having said that, we have had more than 1,000 people register for one or more of the sessions, and thank you for getting involved and doing that. And equally, we've had a fantastic response from people willing and wanting to speak. So we've lined up what I think is an excellent lineup of speakers, 35 speakers from across academia and industry and from around the world. I think we've really put out a good mix. And that includes our chairperson, Professor Tony Wilson of Oxford University, who's given our keynote session talk entitled A Personal History of Confocal Microscopy, which is in session 4 later today. So a couple of procedural things. Questions. We are having, or the speakers are taking questions. We've allocated 5 minutes for the on top of the 15-minute session talks and 10 minutes on top of the longer 30-minute talks. I can already see that a lot of people are using the chat box to say hello. Can I ask that people don't use the chat box other than to submit a question? It is the only interaction that we have with you. So if you can just use the chat box to submit questions throughout the talks, and the chairperson and the speaker will then try and select a number of questions from that chat window and answer them online as I'm talking to you now. So please try and do that. Recording. We're recording the sessions. That includes the chat, so there'll be lots of hellos and good mornings there at the moment. Some of the speakers have asked not to be recorded, and because of that, it may take us a couple of days to edit those out and get them online. However, you will receive links via email to the replays, which you should be able to view at any point in the future, and indeed your colleagues. So, who are Aurox? Well, we were founded in 2004, which may be a surprise to a lot of you. You probably think we're newcomers, but we've been there in the background, steadily developing products. We're a spin-out from the Scanning Optical Microscopy group at the University of Oxford, and we specialize in the design and manufacture of innovative optical confocal imaging instruments for the life sciences, medical, and material market. So how come you haven't heard of us then? Well, I'll come on to that in a moment. So our founders are Dr. Limas Draskatis, who's our Chief Technical Officer, previously at Oxford University. Our chairperson, who I've already mentioned, Professor Tony Wilson, also of Oxford University. And Professor Martin Booth, again, from Oxford University Engineering. And equally, Professor Mark Neal, currently at Imperial College London. So, I mentioned that we were established in 2004. So we've had more than 15 years, getting on for 16 years now, of innovation. During that time, we've developed quite a range of different products that you can see here. And for about 13 years, we developed and built those products purely for other manufacturers. So people like Zeiss, Andor, 3D Histech with a slide scanner system where we provide the confocal module, and also the Zeiss SmartProof 5, which is a materials device used for reflectrometry and surface analysis. Again, using a confocal module produced by Along the way, we've won a number of awards, including R&D 100 Award back in 2010, the Queen's Award, and the Institute of Physics Innovations Awards. In 2017, we decided we wanted to make a step change in our business. We wanted to start dealing directly with the end users and developing products and supporting them in that way. We launched our Clarity product, which is an add-on device to add on to virtually any wide-field microscope, and it's based around, as all of our technology is, around spinning disk structured illumination. A year later, we launched a faster version of that, a high-speed version called the Clarity HS. And in 2019, we launched our own integrated full confocal microscope, which is a benchtop all-in-one device called Unity. So all of our products are laser-free confocal. All of them are spinning disk using structured illumination. We've more than 450 Aurox laser confocal devices sold worldwide. As you can see here, these are our two main products, the Clarity, which I've just mentioned. It's an add-on device, spinning disk. It's designed to go onto any wide field microscope and to provide it or turn it into a confocal microscope. The Unity is an all-in-one system. It includes the laser-free confocal spinning disk system. It includes a light source, computer, everything that you need, a camera. It's all in there in a compact unit to sit on top of a bench within somewhere like a biology lab. So the elephant in the room, COVID-19, obviously it's having a big impact on us. It's the reason why we decided to do this conference. Aurox as a company, we are, as with everybody else, we are working from home if we can, but our production and our R&D are working safely and are still developing and producing products. We do routinely run laser-free confocal demonstrations of our equipment. We have demonstration equipment that goes all around the world. Obviously, that's at the moment a little bit more difficult, especially as most universities are shut down. We have, over the last couple of years, developed a distributor network, and we have distributors in most of countries around the world, or regions certainly. And if you'd like to know more about that, then you can check out our webpage and go to the contacts, and you'll see all the regional, local distributors that we work with. So that really is all I wanted to say. I wanted to keep it short and sweet. You're not here to listen to me, so it just remains to me to say thank you very much to all of you for joining us today. I hope you enjoyed the conference, and I'm just now going to pass over to the session chair, Philippa Timmins. And Philippa, are you there? Aha, you are. Good morning.
I'm happy to come from my phone this morning because my computer is connected to the session. Very typical. So welcome everybody. I'm really glad that you can all join us today. It looks like we have a few people online already. So I'll just wait for Lee to get our first speaker online. So I hope he's in the room.
I think we have Bailey on line. Perhaps we can ask Bay if he'd be happy to speak next, and we can try and work out if we've lost Fujita-san along the way.
Of course, yes, of course. So we'll change the schedule slightly. Okay, so if Bay is available, now we hear from Professor Bailey. I first met Bay when he was a senior researcher in dynamic optics and photonics at the University of Oxford. He's got a vast experience in optics, including work in cars and time-resolved FRET. He founded Hook Instruments in 2017, engaging in R&D and manufacture of advanced optical instruments in conjunction with the Chinese Academy of Sciences. Today, he'll talk to us about applications of single-cell Raman sorting technology in the life sciences. So if Bay can come online, and then maybe we can start his slides.
Okay, I think today my topic is applications of single-cell Raman sorting technologies in life science. I'm from the Chinese Academy of Sciences, and also I'm the CEO in the Hook Instruments. And here is the content of my presentations. Okay, a little delay. I think it's a bit slow, so because from my screen I can't see my PPT.
Okay, so
Can you see that? Is there anybody can see something?
yes, we can see it.
Oh, you can see it.
Yes.
Okay, let me do it one by one because I don't know. I can't see what it is. Yeah. Okay, this is the next page. Okay, here is the Raman spectroscopies. Okay, first I will, I'm talking about the Raman and the single cell sortings. Because we know that the Raman effect was discovered by Indian scientist Raman, C.V. Raman, and he also won the Nobel Prize in 1930s. And I think this is when the photons are scattered by a material, or most of them are elastic scatterings, and so that they have the same energies, and also, but they have different directions. And part of them is elastic scatterings. The energy will transfer from the incident light to molecule vibrations, and also its emitted light have the decreased energies, which means for the different molecule, they have the different vibrational frequencies, and they will just absorb the different energies, and from the wavelength point of view, they have the different spectrum. And for the Raman scatterings, and they have this kind of the features. And first of all, the Raman, they reflect the intrinsic information of the molecules, but they are really weak. And also the light interact with the chemical bonds, so only 1 in 10 to 7 photons undergoes Raman scatterings. So that's the reason why it can, well, the Raman observes this effect, but it's not brought used for a while until the lasers has been developed. And Raman spectra are independent on the incident lasers, and the energy exchange only between the incident light and the chemical bonds. And Raman spectroscopies measure the changes of the light frequencies. And Raman spectra are also the chemical fingerprint. Even spontaneous Raman, and we use that because it just has all information. It's just use the lasers to have all chemical bonds affected, and it have the rich information. But obviously, the signal is really low, and then people just develop the surface enhanced Raman scattering, and also the coherent anti-stock Raman scattering, also stimulated Raman scatterings. And for the source, I think they use a metal surface which enhance the Raman signals, and also for cars and the SRS, they use the pump and the Stokes, which they match the vibrational frequencies of the molecules, and which they enhance the chemical selectivity and the sensitivities. In our case, we use the spontaneous Raman scatterings for the single cell research. And here is the pictures of the single cell. They are the E. coli, and you can see from the right side is the spectrum, the Raman spectrum of this kind of the single cells, and it gives us the qualitative and the quantitative information about the molecule compositions, and according to the single cells molecule fingerprint, and we can just use that to identify the cells, and also can do the cell research.
Hello, Bay. Hello, Bay. We seem to have lost your audio.
In single cells, and also use the whole spectrum as the fingerprint. And we also use the stable isotope probings, and like the carbon 13s and also the D2Os, and we use these probes to effect on the cells and to identify the cells. And also we use the thirst technologies and for the cell research. And in conclusions, we can see that Raman spectroscopy is a non-invasive and label-free vibrational spectroscopy technologies, and it reveals the chemical changes in cells, tissues, or the biofluids, and related with various pathologic conditions in situ, and associated with the multi-variety calibration and classifications algorithm developed on large training data sets. Raman offers a novel and quantitative approach in a wide range of biological applications. And these are because most of our research is based on the medical research, and these are the three kind of Raman spectroscopies we use. And one is in vitro Raman microspectroscopy, because we will take the samples to under the microscopes. The middle one is the in vivo confocal Ramans, and most people use that for the skin analyzers, and they can just use the immersion objectives, and you can just put the samples. You can just directly put the microscopes onto the people's skins and to the samples. And also, people have used the Raman fiber optical probes, and which for this purpose, I think people can just measure the Raman inside the bodies. And okay, this is a little bit introduction about what kind of wavelengths and why we choose this kind of wavelengths, because we know the Raman excitation efficiency is just related to the excitation wavelengths. It's proportional to the force power of the laser wavelengths, and obviously for the shorter wavelengths, it have the stronger Raman signals. But also, for the diffraction limited equations, we can see that for the spatial resolutions, also with the shorter wavelengths, people can also get the high resolutions. But why people don't use the very short wavelengths like the UV is just because we will use that for cells. And first is the photo damage, another is also the fluorescence. Because the shorter excitation have the great change of exciting the electronic transitions in the samples, and particularly for the organic samples or the biomaterials. And so there is we need to choose which kind of wavelengths to use. And here is our testing results, and from my research. And for the bacteria, because usually they are just 1 micron or just several microns, they are very small. So we will use the 532, the green lasers for the excitation, because it gave us more information. But for the cells and tissues, because you can see for the green lasers, it can give us very high fluorescence background, and also the green laser is very easy to damage the cells. So that's the reason we use the 785 for this kind of applications. And for the problems of the Raman, it's obvious that because it's so sensitive, it's very easy to disturbance in the external environment, and also the measurement errors caused by changing they will change the same Raman spectrum. Like if we just use the same samples, even we can find the peak intensity changes, and also we have the spiral peaks and also the peak shift. So that's why we need to use a very efficient and stable Raman instrument and accurate data calibration systems, and plus the precise data analysis software for the Raman applications in life science. And these are the Raman spectroscopies we have developed for the life science. The 532, the upright Ramans, we use that mainly for the rapid identifications of the pathogenic bacteria, and also the AMR bacteria screening and the physiological status monitoring. And the 785, and we just special developed which just to optimize the near infrared detections, and we put that on an inverted Raman microscopes. We mainly use that for the cancer research and also the disease diagnosis. And here is the system calibrations we have used, and we use multiple calibrations to just to make our result repeatable. And you can see we use the cameras, calibrations, the illumination corrections, energy correction, and also the environmental corrections to correct either the background, also the peak shifts. And from the result, we can see we use multiple corrections to make our Raman results is reproducible perfectly. And this is the reason why we can use our Raman microscopies for the cell research. And these are the softwares we have developed. It can do the single spectrum research, and also can do the mappings. And we also developed the image algorithm, which we can extract the content, the samples components. And also we have the large fields and the intelligent image recognition for the very large fields staging functions to achieve the high throughput data collections. And these are the example results. We have used this kind of Ramans for the organism identifications. And we know that usually, I think in the hospital, we want to identify what kind of infections. We either use the culture method, or you use the mass spectroscopies, or I think we also use the metagenomics recently, but they are either to need time, because culture the cells, they need maybe days or maybe months to culture. Even most of the cells, the bacteria, they are unculturable. But for the other methods, they are either the time consuming and also the high cost. So that's why we use the single cell Raman spectroscopies provide the cultivation-free method to investigate the bacteria, which is rapid, easy to use, and non-invasive. And we build this database to identify the pathogens and from the patient samples. And this is another examples, and we have used, and this is AMR bacterial screenings. And you can see in the Raman spectrum for the cells, from the Raman shift, you can see around 2000. I think that's a very quiet place. You know, they are very flat, and we just put the cells into the heavy waters, and to use the Raman deuterium isotope, the stable isotope probing technology. You can see if the cells, they are very active, they will combine with the heavy waters, and you can see a small peak will appear at the 2300 wave number areas, and we can use this to screening the bacteria's AMR. And this is a project we have used, we have developed recently. And this is another examples, and we have used, and we just use that to navigate during the glioma surgery by the Ramans, and we can just distinguish the gliomas and the healthy tissues based on the water content and also the fingerprint biomarkers by the Raman spectroscopies. And okay, I think this page shows why we want to use the systematic study of the single cells, because you can see for the Raman spectroscopies, we will just get the single cell phenotype information, and we know the physiological status and also the metabolic status of the cells. And how can we combine that with the single cell genotypes? So we use the single cell sorting technologies. We establish the correlations between the phenotypes and the genotypes. And this is technologies we have developed, and we use a chip method, because I don't know why on the right side there is a picture to show it should be a small video, but it disappears. It's just we develop a slide, and on top of the slide we have the coatings. And once we put the samples on the coatings, we use based on the laser matter interactions. Once we use the lasers to shoot the coatings, I think they will generate the energies to push the cells away from the chips. And then we put a collector underneath of that, we can get that single cells. And here is the instrument we have developed, and it can be combined with the Ramans and also with the fluorescence, even with the other cell and identifications method. And we can use this with the high precision XYZ stage, and we can just precisely sort the cells at more than 90% accuracies. And these are some of the examples to show how it works. You can see the first column is the samples on the chips. It's an image on the sample on the chip. You can see the red circles. And in the middle column, you can see the cells was ejected by our technology, then it's appear where it is, and you can see the right column, and the cells was collected by the collectors, and this is the image to show where it is on the collector. This is based on the cell shapes, morphology of the cells, and we can also combine the Raman technologies, and we can just still using the technology, we can isolate the cells based on the Raman features. And of course, we can use that on the fluorescence microscopes. And you can see for the first row is just the chip before sortings, and on the bottom row is just the collectors after sorting. You can see the circled cells will be isolated by our cell sorters, and to use these cells, you can either do the DNA amplifications, and also you can culture the cells. And these are the information that we use the isolated cells. We do the whole genome amplifications and to use the cell sorters, and we can achieve the single cell sequence, just only one cells. And also we just use the single cell sortings to culture the cells. You can just these are the yeast, I think, and you can just isolate either one or two cells, and you can see for the petri dish, and you can see the cells can be cultured. And these are the applications for these instruments. And finally, I will just introduce our institute and also my companies. And I'm a professor in our institute, and this institute is called the Optics, Fine Mechanics, and the Physics. It's part of the Chinese Academy of Sciences, and this is the China's first optical institute. And we have the many different research areas about including the luminescence, applied optics, and optical engineering. And we also have the light science and applications journals, and we have 8 master programs, 6 PhD programs, and 3 postdoc programs. And for my companies, and which is founded in 2017, and we mainly engage in the R&D and manufacture of the advanced optical instruments in the biology and applied in the biology and the medicines. And at the moment, we have the product include the single cell sorters, and also the 2 types of Raman scatterings, and also I have the good relationships with Aurox recently. And this is finally, I think this is the acknowledgement, and also we have the positions for the PhD and the postdoc student. If you are interested, and please keep contact me. Okay, thank you.
Thank you very much, Bei, for that really interesting talk. It sounds like you're developing some fantastic methods to use in the fight against diseases such as sepsis, etc. And we're very pleased to be working with you on this, on the future of your technology. So we have one question, if you can hear me, from Karen Ho. She has asked, are the samples to sort ejected from the chip?
Okay, I think you can imagine that for the normal glass slides, and we put the special coatings on top of about the slides, and you just put the samples on top of the slide, and you just, because you can see this is the inverted microscope, we flip the samples and put it underneath the under the microscopes. You can see the cell is facing down, and we will just use ejection cells, and with these cells will just operate it on our coatings, and the coatings will just generate pushing energies, and the cell will just drop to the bottom, and we have collectors waiting there. So this is how it works. Because we have a nice videos, and it's very difficult to explain just by word. And if that person is interested, and I can just show some more interested videos, and that's much easier to understand.
Okay, so maybe I can put Karen in touch with you directly if she has any questions to ask in more detail. Okay. Yeah.
Okay.
we have another question from Ritu Mishra. Does the sorting stress the cells and affect the metabolic status? Did you hear that?
I think the. Oh, sorry.
Did you hear that? Okay.
Okay, can you repeat that?
Yeah. So, does the sorting stress the cells and affect metabolic status?
Okay, I think because I think for because we have the different chips, and we have developed one chips because it's more sticks and there are waters on top of that. I think after that sorting it does not affect, and also most of our applications is just for the single cell sequencing, and for the DNA information I don't think that's having information too much effect. But I think he's right, and if you don't control the laser very well, it's because it will generate the heat, and if you don't generate the heat, laser powers very well, so it might have the effect. But in our case, and we use the pulse lasers, and it's very short period, just in the maybe less than nanosecond effect. So I don't think it's affect too much.
Okay, and maybe one final question, just in the interest of time. This question is from Adarsh Patel. He asks, can this technology is only used for bacteria, or can you sort different types of cells?
Oh, it can just sort the cells based on the cell size. And we use the bacteria for examples, but we also use that to sort the human cells. And we can sell the cells from the 500 nanometers to just maybe 50 micrometers. So I think it can sell the different different kind of cells.
Okay, that's fantastic. Well, thank you again, Professor Lee. We really appreciate it. And maybe we can move on to the next speaker. If anyone has any particular questions they'd like to pose to any of the speakers, oh, we've just got. Then maybe I will pass the questions on afterwards, and we'll try and get them answered directly. Okay, but just in the interest of time, we'll move on. So sorry, Simone. I will put you in touch with Bei directly to ask your questions. All right. So I think that producer Sal is still having problems. So we're going to move straight on to the next. To be from Jeroen Kalkman from TU Delft. So Jeroen has been at TU Delft since 2012 and is also an editor for the Dutch Journal of Physics. Jeroen devotes his research to the development of novel optical instrumentation. He focuses on application areas where optical tomography plays a key role. So today he's going to talk to us about large-scale phase and polarization sensitive optical diffraction tomography. So Jeroen, if you'd like to come online and then get your slides running, we can move on.
Welcome everybody to my presentation. Very glad to be here and to continue our scientific work in this online conference. So let's see. Yeah, all right, this works. So maybe many of you are not so familiar with optical diffraction tomography. So it's a phase contrast tomographic techniques that, well, in the past mainly was used to image very small objects such as single cells, as is shown, for example, here in this work of Carrier et al., or maybe somewhat little bit larger objects such as the C. elegans in the work by Choi et al., where the scale bar is around 200 microns. Or 50 microns, and the entire object is about 200 microns. And it hasn't been applied to very large objects. And only for a particular type of object, such as a plastic lens, it has been applied by the work of Kim et al. In imaging it in full 3D. However, in this case, the object is very homogeneous, and index matching has to be applied extensively to actually make a proper image of that. And so in this work, I would like to show you that you can also apply optical diffraction tomography for large and biological tissues and obtain pretty good images with that. However, we still have to solve a few problems, and one of the problems for large-scale optical diffraction tomography is tissue refraction and scattering. So in the usual case, your rays travel through the object in straight rays. And when, of course, you have refraction and scattering, these rays are no longer parallel, which makes image reconstruction very challenging. So you can do something about it. And the most obvious thing is to apply index optical clearing to reduce the index contrast. However, this also reduces, let's say, the contrast in the image that you want to image in the first place. So you have to improve your diffraction tomography sensitivity to be able to make proper images of that. Also, if you apply it over a really large scale, you have to optimize your field of view over resolution, so your space bandwidth product. And finally, in phase contrast, the resolution is somewhat limited, and we'll also show you that using polarization contrast, you can enhance the contrast in these images and provide high contrast label-free imaging of biological tissues. So we use a standard digital holography setup. So here we have our light source, our coherent helium neon laser, and this light is splitted, and one part goes to the reference arm where we have a piezo stage, and we do phase stepping, and we have a microscope objective in the reference arm as well. And then we have a sample in the sample arm that we can rotate. So we use object rotation, and we have a microscope objective to image the fields from the sample onto a large megapixel camera. And so this creates a very large image of this field with a high magnification, and we need the microscope objective in the reference arm to match the curvature of the field onto the camera in such a way that the frequency contact of the spatial fringes on the camera are limited. Now, to obtain a high resolution over this large field of view, this is a few millimeters, of course, we have to address the fundamental imaging limit. So we have our diffraction limited spot. This is the Rayleigh criterion for that, that we magnify by the magnification of our imaging system. And we have to sample that with at least 2 points per resolution. And if you address that and calculate it for phase stepping digital holography, you need to have an M over NA, a magnification over numerical aperture that is larger than 28. And this is quite challenging if you look at the microscope objectives that typically are available. However, we succeeded in getting close to that. We have an M over NA of about 20. So in total, we can image about a 5 millimeter field of view of the object with about 4 micrometer spatial resolution. And we acquire 1414 projections in about 7 minutes. And then we have a large processing pipeline that we'll briefly go through. So first we get our phase shifted holograms from our phase stepping. Then we can calculate a complex object field. And using this complex object field, we can also do numerical focus scanning, which I will show is essential to obtain high or low noise reconstructions. And if you do numerical focus scanning by applying some propagation to the field, we can actually see that when the object is in focus, the variance of the intensity has a minimum. And since this has a minimum, we can track essentially the focus position when we place the object out of focus. And we can repeat that for a few angles over entire rotation, and we see that the object traverses a sinusoidal trajectory. So we can calculate now the in-focus object field for every angle. So even with placing the object out of focus, we can calculate the in-focus object field. From that, we can calculate the wrap phase, we do phase unwrapping, and in the end get the entire phase sinogram that we can convert to a reconstruction of the refractive index in 3D. And I will show you now that this off-axis positioning is essential to reduce the noise. So if you look at the reconstruction of a typical object, you have two kinds of contribution for the noise. One is coherent noise. This is speckle. This essentially concentrates in the center of the reconstruction. The other one is shot noise, and this is different from projection to projection. So this is smears out over all the lateral positions. And so if you take more projections, you see that the noise floor, this is from the shot noise, actually decreases. However, the noise in the center remains there because it's a fixed pattern speckle noise. And so this is the reason why if we put the object off center, essentially we can reduce the noise by taking more and more projections. And that's what you can see here. And that's what we did. So here you see the reconstruction of an object, and on axis you see that if you increase the number of projections, you don't get any large improvement in reconstruction sensitivity, because the noise essentially is fixed, and it doesn't help if you take more and more projections. However, when we go off axis, so outside of the center, we can really reduce the noise significantly by taking more and more projections. And in this way, we can reach a limit of about 8 × 10⁻⁵ in refractive index contrast sensitivity. And so despite the fact that we do, for example, optical clearing and reduce the contrast significantly, we can still make images because we are very sensitive to small refractive index variations. So I can show you the results. We imaged that for an entire zebrafish, and what you should notice a few things. So here you see 3 cross sections of an entire zebrafish larva, as here as well. But what is important is to note that there's really a microscopic or mesoscopic scale. So we image a millimeter-sized zebrafish. And what is important is that when we look at the distribution of refractive index contrast outside of the zebrafish, we see a distribution that is actually very narrow. So we can actually measure refractive index differences to a very high significant sensitivity, which is essential to still make images of the zebrafish where you can delineate all kinds of aspects of the tissue morphology. So having said that, of course, these images look nice and we can discern a lot of features in these zebrafish, but the contrast is still a little bit limited in that sense that we only see certain features, and we would like to have more contrast in these images. And that therefore we applied polarization contrast ODT, optical diffraction tomography. And essentially what we did is we added polarizers before and after the sample, and also in the reference arm we added a polarizer and a wave plate in the source arm to control the polarization. And the basic idea here is that if the object is birefringent and we put polarizer P1 and put P2 in a cross-polarized state, then we would see some intensity images on the camera. If the object is entirely without any birefringence, then there's no light passing through polarizer P1, polarizer P2, and the image on the camera is entirely dark. This is the basic principle of polarimetry, and this is what we apply here in optical diffraction tomography, where we can now use all these tricks that diffraction tomography allows you. So this numerical refocusing and image reconstruction in 3D. So the basic physics behind it is a little bit more complicated, so we'll briefly go through it. What is most essential is that we have a sample arm where we have a cross-polarized polarizers. So these polarizers P1 and P2 are cross-polarized, and that we have an object, which is maybe a fiber, that is located relative to the plane of the polarizers with the angle phi and alpha. Secondly, we also rotate the object along the x-axis, so we also have another angle. This is beta. And finally, we have also a polarizer angle rho. So all these angles, they are intermingled with each other during optical tomography. However, we can still make appropriate images with that. So our basic flow is that we measure, we define the mean phase. Because we now have a birefringent material, we have NE and NO, the extraordinary and ordinary refractive index. And we also define the birefringent phase shift. And the birefringent phase shift is now also dependent on this cosine squared of alpha, which is the angle of inclination outside of this polarizer angle. Note also that this alpha again depends again on the rotation angle in tomography. Now we can calculate the entire complex transmitted field through the object as been shown here. So it has a few components. So here is this parallel polarized component, and here is this cross-polarized component. Now, as you can see, if there's no birefringence, delta is 0, and we only get this term, which we can select, and we can do ordinary phase tomography with that. If we do have birefringence, delta is non-zero, we also can analyze the second term, the y component. And so if we first look at the parallel component, we see we can get an expression of the phase of the field, and we can take a derivative of that and look what the phase of that field is, and we see that it's approximately proportional to the inverse tangents of the mean refractive index. So this first term is what you usually use in ordinary phase tomography. Also, there's a second term that depends on the birefringence delta, and this is shown here. But in general, this term is much smaller than the first term. So in parallel polarization, we can just do ordinary phase tomography. If we now look at the cross-polarization term, we see actually that it is now the amplitude that is of interest. And for this y component amplitude, we see that it is dependent on the sine of delta over 2 in absolute terms, multiplied with the absolute terms of the sine of the rotation of the polarizers with respect to the orientation of the fiber. Now we can invert that, and for arbitrary delta, we can actually want to extract this delta, but we see that it has a lot of wrapping. So there's first a wrapping or a mirroring around phi equals to pi. This is an example for a homogeneous cylinder. There's first a wrapping around phi is pi, but also a wrapping around phi is 2 pi. So this is actually quite complicated situation for arbitrary large delta, but unfortunately for biological samples we have rather small delta, and even for the case where we use optical clearing, so we can make a small delta approximation. So we can essentially assume that this sine, inverse sine of the sine, is close to delta for small delta. So the entire process flow now looks like this. This is the ordinary phase signal process flow, but we add a few additional features. So we have a measurement with parallel polarizers. This is our original phase reconstruction, but we can also measure it for cross polarizers, and we do that for 3 different orientations. Now, furthermore, we can do all the same processing that we did for phase processing, but then if we now calculate the in-focus field, we can make a calculation of the amplitude and the phase projection. And in this case, we accommodate for the orientation effect of the optical fiber by taking the highest value of delta that we obtain for our amplitude reconstruction. And finally, we can reconstruct the phase as we would ordinarily do, but also reconstruct this amplitude delta and create also a sinogram for the amplitude. From this, we can calculate our ordinary refractive index difference, image, delta, and average. This is now our mean refractive index optical tomogram, but we can also obtain a scaled birefringent image, NE minus NO. Now, similar as to what we did for phase tomography, we can also increase and improve the sensitivity for polarization contrast. So also there we see in the center an increase of the noise. Here is the noise for polarization contrast, similar as we see that for phase tomography. You see here the noise in the mean refractive index. So we see in the center that's more noise, and we also use off-axis placement of the sample to further reduce the noise also in these polarization tomography reconstructions. And so to obtain high contrast, high resolution images. So finally, here is the initial results. So here you see the conventional phase projections at the bottom. So you see here there's the zebrafish tail right here, but you see that the phase contrast is not so big, because here you in the background you also have, of course, a constant phase background, and also here, and the phase contrast you obtain for the object of interest is only slightly larger than the background. Now that is in contrast to cross-polarizer amplitude, where we are sensitive to the birefringence. Everywhere where there's no birefringence, the projection is entirely dark. You cannot see anything. But in case where you see, in this case, the myotome, the muscle structure of the zebrafish, you clearly can see a large intensity popping up where this birefringent tissue is present. So here you see one projection, and here you see a second projection, and also you see that here in the histograms. So this essentially shows you that you are very sensitive to measuring actually the birefringent tissues. And we can also do that in 3D. So first here you see the phase contrast reconstruction. Here we take one cross section, and you can see that there's the median fin folds, the notochord, and the spinal cord clearly visible. But in the cross section of the entire body of the zebrafish, you don't see that much contrast. If we look at this polarization contrast image, we now have a clear picture of all the muscle tissue that is present in this muscular birefringent tissue. And so you see that, of course, we see the same tissue also in phase contrast, but we don't see it delineated from the surrounding tissue. So this gives you really an added value to really be able to observe birefringent contrast tissues. And we can also, of course, also combine them with artificial coloring. So that brings me to the end of my presentation. So I hope to have shown you that large-scale phase and polarization ODT are possible. We have shown ODT with large number of projections and off-axial sample placement to really enhance the sensitivity and reduce the noise. Also, after optical clearing, the phase and polarization contrast remains sufficient for identification of relevant structures in tissue. And finally, polarization contrast optical diffraction tomography gives high contrast images of the fibrous structures in biological tissues. So with that, I would like to end. Thank you for your attention. Yeah, feel free to contact me if you have any further questions. And I'm now open to accept any questions of you. Thank you.
Okay, thank you very much for that really interesting talk. It sparked quite a lot of questions, actually. So we'll try. So can you hear me, Jerome?
Yeah, I can hear you.
Good, good. So the first question, I hope that I pronounced your name correctly. It was from one of your earlier slides. What is the limiting factor of the speed of acquisition? Is it the piezo stage speed, the camera, the sample rotation, or is it the low signal?
It's a good question. So in our current case, it's the camera acquisition speed. It's, I think, at maximum 60 frames per second, and actually we need quite a lot of phase shifts and projections and polarization contrast to acquire these tomograms. So that is quite let's say, yeah, we need quite a lot of information to reconstruct that.
Okay, and another question from Izzy Prankard. What optical clearing method do you use?
We use BOP, Murray's Clear.
Okay, okay, nice, concise answer.
It's about 30 minutes, and then becomes really optically clear, sufficiently optically clear to apply this method.
Okay. And another question from Mohammed Azizian. Considering the compressive sensing, is it possible to include some degree of sparsity in your acquisition?
Add sparsity. Well, I think so. We haven't we still use kind of the old-fashioned filtered back projection, which of course is robust, but possibly can be improved significantly and quite a lot. Yeah.
Sure. A question from Ben Sutcliffe. Could the processing principles be applied to multi-view light sheet microscopy?
Yeah. Let's see. Well, I think so. In general, I think we're actually closing the gap between what were two completely different technologies, and maybe combining them into a kind of one framework. But yes, in principle, that's possible. Yeah.
That might be a good conversation to have offline between you. So maybe Ben, you could get in touch with Joran directly.
Yeah, although maybe as a short comment. So of course we use label-free imaging, and we use the fields that we acquire. In that sense, it's not compatible with fluorescence imaging.
Sure. A question from Azamet Tadesse. What kind of illumination pattern is used to get the many holograms? Maybe you could explain a little bit more about your illumination.
We just use a plane wave illumination, so there's not much any special illumination patterns. We only need to make sure that we also apply a microscope objective in the reference arm, because otherwise we get a really high field curvature on the detector, and these fringes we cannot resolve, and this will lead to error then. So the microscope objective in the reference arm is just for making the field curvature much flatter.
Right. And then just maybe a couple more. That, as I say, your talk sparked a lot of interest.
Well, very good.
So from Lucas, what kind of compensation systems do you apply in the system in order to reduce the impact of mechanical vibrations?
That's a good question. Actually, none. So we feel that we're not so sensitive of it, because we have a good optical table, and we usually don't see any problems with that. So the speckle is also mostly really fixed pattern speckle, and we don't see anything moving off on that. No.
Okay. Is it possible to observe live samples from Alexandra Benedito?
Well, I think that's the most intriguing question. I think it's a nice road ahead. What I view, of course, is the difficulty is if you want to image these kinds of samples that have this size, then that is really challenging, because then you will have scattering and refraction playing a big role. So maybe I think it's the road ahead for smaller samples to apply these kind of technologies for that, and to see whether you can really, because you acquire the entire wave field, you might also use that to fully correct for aberrations, correct for refractions, and even do full wave field reconstructions.
Okay. A question from Feng. I'm not sure I understand the question, but maybe you will. Why the phase warp procedure is inverting the signal, not subtracting a constant?
I think I'll have to discuss that at a later stage in more detail.
Okay, a bit more in depth.
Alone, I cannot really understand it.
Sure. Maybe we could put you in touch.
Sure.
Sebastian, how long will a single scan take? I think you might have touched on how long things take in one of your slides.
Well, in the phase tomograms, the entire data acquisition is about 7 minutes, and still, we have tons of data, so our processing pipeline is not really fast, but we're working on that, and I think that could be in the order of multiple, maybe tens of minutes as well in the end. Right now, it's taking multiple hours, but we can process it in quite a bit of more efficient way.
Cool. And the very last question from Alessandro. what are the main advantages versus optical projection tomography? He says he's not an expert, but he sees some similarities.
Well, yeah, that's a very good question, and we have looked a lot at previous work on optical projection tomography and also on polarization optical projection tomography. Well, I would say the big advantage here is that, well, since you are measuring the entire wave field, you can do a few tricks that are helpful. So first of all, you can play around with the wave field to, for example, do numerical refocusing. That is one thing that you can do. You can maybe also improve the resolution by, for example, depth scanning or region of interest focusing. And I think the first addition is this refocusing allows you to obtain potentially a better signal to noise ratio, although that is of course still a matter of research that we have to compare these two methodologies.
Sure.
And finally, it's label free, so that's well, OPT can also be label free in bright field, but usually it's used in fluorescence, and we are aiming for label free imaging.
Sure thing. Okay, well, I think we better stop it there in respect of time. But thank you so much for joining us today, Jerome. It was a really interesting talk.
Okay, thank you.
Do stay online. Oh, we have somebody wanting to contact you offline about an extra question. So we'll put you in touch later.
Sure.
So thank you again, and we'll move on to the next speaker. I believe that Fujita-san is now available.
Thank you.
If you can come online and turn on your video and audio and then your screen share, and we can get you up and running. So just as a recap, it's my pleasure to introduce you to Professor Katsumasa Fujita from the Department of Applied Physics at Osaka University. His research interests include super-resolution fluorescence microscopy using saturated excitation of fluorescent molecules and Raman microscopy. Today, he's going to present some of his work on imaging small molecules by Raman microscopy. So over to you, Fujita-san, if you can turn on your audio and video.
So I really appreciate the organizing this conference, because we are going to organize FOM 2020 in Osaka. But of course, as you know, it has been canceled because of this Corona issue. So instead, we have many audience in this conference. I'm really happy to present our recent work on Raman microscopy. So I'm Katsumasa Fujita from Osaka University, and we've been working on Raman microscopy and its application for more than 10 years. So as you know, the optical microscopy is a key technology for bioimaging, and I don't have to explain everything to you. But of course, this is very useful too, but it's not perfect yet. So especially on the meaning of this target of the bioimaging is still limited. So this is actually an example that people usually cannot observe by fluorescence microscopy. Those small molecules actually just too small to observe, like nucleic acid, lipids, drugs, saccharides, peptides. So if you compare the size of these small molecules with the fluorescent dye using fluorescence microscopy, the labeling of these molecules by the dye molecule changes the chemical property of them a lot. So even though you apply the label of the small molecule into your sample, the responsible cell or activity of the molecule are totally different. So today, I'd like to introduce our recent attempt of observation of this, to observe this molecule by using Raman microscopy. And so we've been working on Raman, development of Raman microscopes for many years, but basically it is a label-free technology. But if we combine it with labeling or tag technology, we call it Raman tag, so we can have approach to observe these small molecules. So let me start from our Raman microscopy techniques. So So this is the diagram showing Raman scattering, and so the Raman scattering is this spontaneous scattering process. So it reflects the vibrational energy state in the molecule. So after the incidence of light into the molecule, some part of photon energy moved to molecule by exciting them to the molecular vibrational state. Then the loss of the energy actually can be observed by a change of wavelengths, as a change of wavelengths in the scattered light. And we can calculate how much energy is moved, which actually corresponds to the structure of the molecule, the photon excited. So this is typical Raman spectra we obtain from a mammalian cell. So in this case, a HeLa cell. And we use, in this example, we use 532 nanometer excitation and detect it from 550 to 640 nanometer. And as you see here, there are many different peaks that corresponds to the vibration of molecules. And we can use this rich information to investigate cells and, of course, to image cells. And in Raman imaging, the principle is really simple. So if you have sample, you just measure the Raman spectra at every single point of the view area. So as a result, you obtain this 3D dataset, that XY spatial and also Raman shift spectral dataset. And then by choosing the Raman peak of your interest, you can reconstruct the distribution of the molecule that showed this that showed the Raman peak chosen. And these three typical examples we always observe. And the 750 is this is assigned to pyro ring bridging mode, especially contained inside chromes, and it's a part of HEM. And the 680 is 1683. So this is a vibration mode of a peptide, and it's called one of the vibration mode of a peptide bond, and especially seen in the protein beta seed. So beta seed is spread everywhere in the cell. So we have signal from entire cell body like this. And the 2050 is assigned to CH2 stretching mode. And since lipid molecule contains a lot of CH groups, so we have a strong contrast of lipid droplet, and also the from the membrane of organelles, especially in this case mitochondria, is imaged. So in the Raman microscope, we basically don't need labeling to observe, to identify molecular species roughly, and obtain the spatial resolution in them. Of course, in this case, diffraction limit resolution. So, but the problem, the issue of Raman microscopy is a small cross section. The efficiency of Raman scattering from molecules is really small, and the typical value is 10 to the minus 30 square centimeters. So if you compare this with the absorption cross section of fluorescent molecule, you can imagine how small the efficiency is. So this means the number of photons you can detect in the observation is really small. So we need a high power and also long time accumulation. And this is an example. In the moderate laser power, like less than milliwatt in the focus, and to get this kind of Raman spectra, it takes about 5 seconds. And if you obtain to 128 pixel, it takes about 23 hours. So this is too slow for live cell imaging. So what we tried about 10 years ago is implementing this line illumination. So this idea is simple. We just parallelize the detection of Raman spectra. So in this case, about 120 points, pixels. And the simple expansion of the 1D focus actually allows the speed of the image acquisition more than 100 times. So we are basically using this system, this simulation scheme, and developed the optical system about 10 years ago. So then this is our setup. We have a CW laser, and the line shaped focus is produced by cylindrical lens. And this line focus shape is used as an illumination sample by projecting it to the sample like this. And the Raman scattering from the line is imaged onto the slit of the spectrophotometer. So in the spectrophotometer, the Raman spectra is separated into space on the CCD camera. So on the camera, we have 1D image of a hyperspectrum, hyperspectral 1D image of Raman scattering. And then we scan the line to one direction to obtain 2D distribution of Raman spectrum. So this is another example. So this is again HeLa cell, and then for obtaining the sample, so it takes about 5 seconds exposure time per line, and we scanned 120 positions, and the acquisition time is 15 minutes. So the time is still much longer than fluorescence imaging, but this for some application, the speed is fast enough. So we, after building this, we performed several applications like observation of cytochronicity dynamics in apoptosis, or osteoplasm mineralization, or cell division. Those cell responses are so slow, so we can still follow the molecular dynamics by Raman microscope. Then we next, as a target, next application, we targeted small molecules. So since, as I explained, fluorescent microscope cannot image them. So maybe Raman can, because Raman detects vibration of molecule. So however, in like sample like cell, we have many different molecules, and they are overlapped in this, the so-called fingerprint region. So actually, the information is rich, but we cannot extract a particular vibration or particular target unless it is very strong. So however, so we changed the strategy. So, but rather than using this fingerprint region, so we try to utilize the silent region. So this silent region, it does not have a strong Raman peak. So this N2 peak is actually not from sample. This is from our optics. So compared to the fingerprint region, so there's no many overlaps. So this means this region doesn't have any information about sample. However, there are some molecular groups that gives a Raman peak in this region. So one of them is the alkyne. The alkyne is a CC triple bond, and this CC triple bond stretching vibration gives Raman peak at 2100, 2200. So we propose the use of this alkyne as a tag of small molecule. So this work is a collaboration work with Recon group, Professor Drag group. So they are synthesis chemistry, and so we have been collaborating with chemistry and also microscopy to explore this imaging modality. So this alkyne tag, as you see here, the structure itself is really small, and the smallest alkyne is 2 carbons and 1 hydrogen. So the interference of this group into the target molecule should be much smaller fluorescence molecule. So as a first demonstration of this technology, we chose this deoxyuridine targeted by alkyne. This is called EDU. So, and we measured Raman spectra first. So as you can see here, this EDU has strong alkyne peak in silent region. But of course, the deoxyuridine does not have. And so this should be able to be separated from the endogenous cell Raman spectra. And now, as a principle of concept, so we did a simple experiment. So we cultured a HeLa cell together with this EDU, and then what we expected is this EDU will be uptaken into DNA because the structure is very close to thymine. And actually, this effect is already had known. So if this is successfully taken into DNA, and so in such condition, the signal of alkyne should come from the nucleus. So this is the result. So this is Raman images of HeLa cell. And the incubation time is 6 hours. Then we scanned by our microscope. And as you see here, at 2123, we find a clear peak of alkyne, clear signal of alkyne, and this is localized intrinsic as we expected. And 2023, sorry, this is no, without EDU, we have no signal from the same wave number. So this is the first demonstration of alkyne tag imaging of small molecule. And we also investigated different groups, molecular groups, and like nitrile, azide, and CD stretching CD groups. So then we compare the signal, and so from this simple comparison, so the alkyne and nitrile give a good signal, and also the CD stretching mode also has good signal. If you accumulate them, so that the strength, the signal amount should be sufficient. While the azide, this also have a peak at the side region, but this peak will be too small to be used as a tag. And we also synthesized, one of our postdocs synthesized 80 different molecules, and they found some trends of the strengths of the tag signal and also Raman shift. So by using this table, we can actually design the Raman tag for your target molecules. And one of the typical, the important feature is here. So if you have aromatic ring, which is in your target, the strength of Raman becomes nearly 10 times larger. And you have more alkynes, of course, the signals become higher. So we can actually design your tag by using this table. And we synthesize this ubiquinol analog, and this has actually two alkyne, okay, and it have such a different Raman shift. So we can perform multicolor imaging of Raman tags. And we performed this kind of small molecule imaging and drug imaging, and also repeat imaging, organelle imaging. So basically, we can transfer the idea of this Raman tag technique to fluorescent labeling technique. So we haven't fully explored what we can do with this Raman tags. However, there are many other groups also are now investigating the application of these tags. And this is a picture from review paper from Columbia University Wayman's group, and they summarized the application of these tags, and actually there are more recently. So one of the issues, actually this is the biggest issue probably in this technique, is actually sensitivity. So as you can imagine, Raman scattering is very weak. So the detection limit in concentration of the target molecule is actually high. So in this EDU case, we measured Raman spectra and different concentration and expert time 10 seconds. And from this data, we conclude that we need about 200 micromolar in your sample. And this is actually very high. And the application we can perform at this moment is only for the target that can be accumulated into the sample. So some application like drug imaging, this concentration is too high. So we need a technique to enhance the sensitivity. This work is basically done in Osaka University, but we also thank many collaborators for brain imaging and alkyne imaging with our other group in Osaka University and Riken. And thank you very much for your attention.
Thank you very much for such an interesting talk. Can you hear me okay?
Yes.
Yes, good. Okay, so we have a few questions that have come up in the chat folder. So a couple are quite similar. So Mohammed asked how deep can you image into a sample? I think you answered that a little bit, but can you image in 3D? How deeply can you image into, say, the brain slices?
Okay. So since our Raman microscope using spontaneous Raman, and as I said, it's so weak, so we actually cannot go deep much. But single or double layer, I would say, like 10 to 20 microns would be okay.
Okay. And Paulina has asked, is the alkyne group toxic for the cell? What happens to the small molecule tagged with the alkyne once it enters the cell? Is it metabolized? Okay,
so I think it's alkyne group itself is not toxic, but the molecule tagged by alkyne behaves differently, of course, because it's not a completely same as the original molecule. So some the biomolecule we tagged actually can be toxic. I mean, cell stop differentiation, but of course, depending on the position, it changes. And as a drug, for drug imaging, we tested the efficacy of the drug first. So after synthesize the drug, we tested this drug, and if the effect is the same, we perform imaging. So we need, of course, special care of preparing the target molecule.
Okay, and I think that answers the question for Morgane as well. She asked, is the functionality of the alkyne tagged molecule altered? And you said, yes, it is. Okay, from Alexander, how constant are conditions for the gold nanoparticles in the cell? Do particles aggregate and influence the Raman signal? Do you need to have individual gold nanoparticles for reliable measurements?
It's a very good question. Actually, that's most difficult part of the application SAS. And so it's not stable. I mean, gold itself is stable, but the aggregation condition changing in time. So the enhancement changes. So, but the reproducibility of data is high. I mean, as I show in the movie, it's a frag blinking and the signal also changing. It is always like this. So if we have a way to handle this fluctuating data, it should be useful. So one of the example is discounting the source spot. So actually, so this count if the number of the target is small. So this can be quantitative. And the recently one the paper published in Nature Nanotechnology on this technique. So I think so the signal processing may solve this issue.
Okay, we do have quite a flurry of questions. I'll try and get through a few more before we finish. What is the temperature dependence of drug uptake at higher concentrations?
We just performed the two temperature, room temperature. Sorry, not was. Yes, 37 and 4. For this drug, there's no temperature dependence.
Okay.
So, but for some, yeah.
Okay. And from Mika, he says, very cool. Does the metabolic labeling with EDU have any undesired effects on background? How long will you need to wait for full incorporation of the label to the targets?
We haven't tested. Sorry, I don't have a slide here. For culturing for hair cell in the cell, actually, I think the speed depends on the DNA synthesis, and in our experiment. Okay. Sorry, I actually don't remember exactly, but probably 12 hours was enough for all the cells in culture incorporate the EDU molecule.
Okay. In the interest of time, what we will do, there were quite a few questions came into the chat folder, and I will try and put people in touch with you directly, so they can discuss that with you, if that's okay. Because there's another sort of 10 questions that people want to ask, but we will run out of time. So thank you so much again, Fujita-san, for joining us.
Thank you very much.
Enjoy the rest of the conference and stay safe.
Thank you.
Okay, goodbye. Goodbye.
Bye.
All right, so if you heard me, everybody that's into the chat folder at the moment, we'll pass these questions on to Professor Fujita-san for him to answer at a later date, but we will run out of time if we carry on. So do we have Rakesh online?
Yes, you do. Can you hear me? Hello?
Rakesh?
Hi, can you hear me, Philippa?
I can't hear your audio.
Okay, bear with me.
Interesting, I can hear you.
Oh, okay.
Okay.
Yep, I can hear you now. I think that's fine.
Okay, so I shall turn on my screen share.
So just as a quick introduction, so this is Rakesh Saman from Tomacube. Rakesh received his PhD in Alzheimer's disease research in 2013. I first met Rakesh when he was working for Phase Focus, but now he's the senior sales and applications specialist at Tomacube. Tomacube manufacture a range of hollow tomographic microscopes for label-free imaging, and Rakesh will now give us a taster of what they have to offer. Okay, over to you.
Excellent. So this is indeed a taster. I've got 15 minutes to tell you as much about hollow tomography and Tomacube as possible. So I'll get on with it straight away. So my talk is titled Hollow Tomography, the Next Frontier in Live Cell Label-Free Imaging. So I'll take you through a little bit about hollow tomography, the background, and some of the applications that it's being used for. Okay, hollow tomography is a label-free imaging technique, but label-free imaging is not an old technique. It's been there since bright field imaging, you could argue. But there's always been a quest for contrast. So we've always wanted more and more contrast. I mean, we had this big step change when we got to fluorescence microscopy. We can finally see that huge signal with low background noise. But when it comes to live cell imaging, and especially in 3 dimensions, labeling of the cells can be challenging. So just taking, for example, a conventional confocal microscope, sample prep can be difficult for live cell labeling. There is always going to be an element of phototoxicity, either by the illumination or by the labels being present themselves. We've seen in the previous talk how the label can have steric hindrance or can alter the cell itself. Unless you carefully consider your experiments with confocal fluorescence microscopy, it will be qualitative to some degrees, and imaging times can be long when we consider multiple channels and multiple Z sections. So in the last 10 years, there has been an emergence of a new field, which is quantitative phase imaging. And you can see with quantitative phase imaging, without using any labels, we can achieve the same level of contrast as you see in a fluorescence image, as you can see in this image in the top right here. And where Tomacube come into this is they developed hollow tomography in their microscopes in around 2016. So they're very new in the world of quantitative phase imaging. But the big difference with hollow tomography is it's not 2D. Hopefully you can see these videos playing. What you can see here is that the data set we get from a Tomacube system using hollow tomography is 3D. You can see that Z slicing in the top left panel going through a data set, and the contrast you're seeing here is the refractive index measured at each voxel. Over on the right-hand panel, what we can do, we can take bands of these refractive indices, and we can use that as a lookup table to color different parts of the cell. So the membrane, nucleus, cytoplasm will all have different refractive index ranges. So the key word is also quantitative as well. So the technology is quantitative. So we can give you a morphological, a three-dimensional morphological phenotype through surface modeling, but we can also tell you information about the cell itself. So the mean refractive index of the cell, the concentration of proteins within the cell, the dry mass, etc. And again, you can see some of the refractive index ranges on the right and how they relate to different parts, different organelles of the cell. So how does it compare? So holotomography, there's no labeling required. There's no phototoxicity because there's no labeling, but also the light powers used are minimal. It is quantitative. We saw that on the previous slide. And what's impressive is this is ultra fast. So there's no Z sectioning required for the holotomography. This data set, this 3D data set, takes 0.4 seconds to acquire. So you can run at approximately 2.5 frames per second. So the microscope I'll be describing mainly today is the HD2H system. Just a few highlights here. We use 60x objectives, which has a numerical aperture of 1.2 and a water dipping. We can achieve a resolution depending on the sample type up to 100, as low as 110 nanometers. And the speed here is really important. For a 3D data set, we can operate at 2.5 frames per second. But that doesn't discount the two-dimensional phase imaging that we can still perform. We can still perform 2D phase imaging on axis at 150 frames per second. So what is holotomography? You can see by the name that it is holography is an element in there, and it's a type of phase imaging, is holographic imaging, where we are detecting the phase shift as light passes through the cell. There's two features of the cell that will cause the phase shift. That is both the refractive index and the thickness of the cell. And the holographic principle in holotomography is applied in the very same way, where we take a sample and a reference beam to produce a hologram from which we retrieve the amplitude and phase information. Where things differ from two dimensions is the way we rotate the light source around the cell. So similar to CT scanners, we also rotate the light beam around the cell, and we collect holograms at multiple angles. And this is what's done cleverly within the system. Using a digital micro mirror device, we can change the pattern on this mirror without any mechanical movement or vibration to collect 48 images around 360 degrees. So these 48 images around 360 degrees are acquired in that 0.4 seconds. So it's that speed element which this DMD mirror really gives you here. So then it's over to the algorithms. We've seen a lot of physics, and unfortunately I'm not a physicist, so this bit will be quite light. But we do then put these all the information from all these angles into an algorithm, which then gives us, most importantly, the refractive index and the 3D shape. So the phase shift due to either the thickness or the refractive index of the cell are decoupled. So we now have a refractive index map, a 3D refractive index map of the cell. And just to demonstrate this, a typical 2D phase, quantitative phase image would look like this, where it's essentially a max intensity projection of a 3D image. But using holotomography, what we achieve is the information in 3D. You can again see that in the slicing in the top left panel, but also in the YZ and the XZ plane as well. And just on the right, we have the refractive index lookup table as well. So the HD2H system is unique in that it combines 3D holotomography with 3D fluorescence. We have a deconvolution plugin within the software, so we can take multiple fluorescence images at different Z sections and deconvolve that image. So that enables us to verify refractive index features that we see in the holotomographic image. So in this example here, we have HEC293 T cells, and they are transfected with MitoTracker. And you can see where the features of the MitoTracker align with the two-dimensional holotomographic image. So again, just like before, we can render the different refractive indices to show the three-dimensional nature of the cell and pinpoint where the MitoTracker lies within that 3D volume. So I'll next go over a few applications, some of the imaging candidates and applications. So in terms of samples, we can image a wide variety of cells, so your conventional mammalian cell lines. But also, because we have that 60x 1.2 NA objective, we can start to image things like bacteria and yeast. So we can go to the smaller sample size. And this is a nice example of yeast of bacteria cell division. And we can clearly see the cells, bacteria cells divided. But what's really nice here is with the refractive index information, we get a little more detail. We can see that during cell division, the one part of the cell, the high refractive index part of the cell, is polarized. So the bacterial cell keeps this polarized section during cell division. I mean, with looking at bacteria, this was taken further in this paper here, where different Bacillus subfamilies were identified just using holotomography. And as you can see, they was able to successfully separate out, in this case, anthrax and non-anthrax populations of Bacillus. So we saw a little bit of nanoparticles in the previous talk, and this is a perfect application on holotomography as well, because gold nanoparticles, silicon metal core nanoparticles in this case, will have a unique refractive index. We can track those, therefore, in that 3D volume. We can easily select that refractive index band of those nanoparticles, and we can see where those nanoparticles are being delivered into cytoplasm or into a nucleus, etc. Inbuilt into the Tomocube microscopes as well, we have a movement of the stage where we can collect multiple positions. This enables us to collect bigger fields of view, so we can do seamless stitching to collect a bigger field of view. And this is a nice stitch data set. This is not just in holotomography, it's also in the deconvolved images as well. We can have that very good stitch data set. And just a nice example of a merged holotomography with a 3D fluorescence data set. This is particularly important in applications such as neuroscience, where we want to look at the neuronal projections over a larger area. And as you can see, this is a nice example of a cortical neuron, but we still retain that high resolution even at this very large field of view. So we can see, we can zoom in further and we can see the details on this neuronal projections and the features on this as well. And what's always important to remember, this is not just a two-dimensional image. Even in that large field of view, this is a three-dimensional data set. So this is a 3D data set of a large field of view of that cortical neuron. I mentioned at the start of the talk that the technique is very low, where the toxicity is negligible, if you like, in holotomography. So this makes it very suitable for time-lapse imaging. And with time-lapse imaging, you see different things depending on the rate of imaging. So this first video here is time-lapse imaging at 90-second intervals. And we can see quite nicely chromosomes aligning on the mitotic spindle. We can see them separating into what's to become the two daughter cells, and we can see the refractive index of the contractile ring as well. So we go slightly faster. We can go now to 2-second intervals, and we start to see things that are slightly different. We start to see more detail. We start to see the ruffling of the membranes on the membrane edges. And in the bottom right here, you'll also start to see the chromosomes starting to assemble before they form the mitotic spindle. That's coming up right here. So you can see all the chromosomes beginning to assemble. So then, moving to the fastest three-dimensional imaging we have with holotomography, this is the HEC293 T cells, and this is imaging every 0.4 seconds. And now we're looking at a very different dynamic within the cell. We can't see much movement on the membranes of the cells, but what we're seeing is a lot of movement of particles within the cell. So we can see a lot of these high refractive particles, most likely lipid droplets, whizzing around this HEC293 cells, or two HEC293 T cells. You can see two nuclei here. So again, it's important to remember, even in these high frequency 3D time-lapse data sets, it is a three-dimensional data set. So we can render the surfaces, and we can render the refractive indices around those high refractive particles in the cell, and therefore we can track the movement of where these high refractive index particles go. And it's quite nice to see, even in the YZ plane, the fidelity of the data. We can see these particles whizzing around in this YZ plane, so really showing the true 3D reconstruction of the data set. But that's one side of it. We see all these nice, pretty pictures, pretty videos, but we need to quantify. We need to get some data back. We need to publish this this type of work with numbers. So I mentioned before we can do 3D morphology, so we can render a 3D volume around the cell, and we can then calculate the 3D morphological phenotype. And this is an example of a HEC293 T cell that was alive, and on the right, it's a HEC293 T cell that was fixed. And just plotting some data from this one, what we can see is that the fixed cell has a higher refractive index compared to the live cell. And this is probably to be expected due to the cross-linking of all the proteins. So it's just an example of how we can use a 3D morphology and still use the refractive index information as a quantitative measure. Another example where quantification has been applied is in the CAR T cell assay. So here you see in suspension a cancer cell and a CAR T cell, and as the synapse forms, you will see that the cancer cell starts to bleb, so it starts to induce apoptosis. So you can see the blebbing right here. Again, we see this beautiful event happening. We see the positive interaction of the CAR T cell and the cancer cell, but we need to quantify that somehow. And this was done in a paper that's on bioRxiv at the moment. And the group here used machine learning to first identify the cancer cell and the CAR T cell, and also identify the synapse formation. So in this video here, you'll see the cancer T cell and the cancer and the CAR T cell. But what's impressive here is we can orthogonally slice the image and focus in on just the synapse, as you can see in the bottom right-hand corner. So we can measure what's happening at an active synapse. And therefore, we can, once we have that information, we can start to quantify that information. We can see that once the active synapse is formed on an antigen-presenting cell, we have an increased area of the synapse area. So we have a positive synapse. We can differentiate the activity of this CAR T cell. And you can also see changes in protein density as well between the active synapse and a non-active synapse. So that brings me to the end of the 15 minutes. And I've just shared a couple of quantitative examples here, but there are much more examples. There's a big publication list on the website, some very recent publications this year as well. So that brings me to the end of the talk, and please do ask questions now, but also get in touch with me, and feel free to visit our website as well for more information.
That's great. Thank you very much, Rakesh. You did get quite a few questions, and I think I'll just ask a couple in the interest of time and put everybody else in touch with you. So the first one is from Jan. How does Tomocube take care of reducing speckle noise that is usually associated with laser-based illumination?
Unfortunately, Jan, I'm not the best person to answer that question. This will be something for our professor Paul Park, who's our CTO, and certainly I can find the answer to that question for you from him.
Okay, we could put you in touch later. And from Roland, do Tomocube systems and other label-free systems based on typography at IG, i.e. phase focus, have different applications, i.e. how do they differ?
Yes, so the applications differ quite vastly. Tomocube will offer you a 3-dimensional data set. So with phase focus, you're dealing with 2-dimensional quantitative phase imaging, and whenever you see an image, you can never be sure whether the contrast you're seeing is due to the refractive index or the thickness of the sample of the cell. But with hollow tomography, we do have that 3D information, and we can report the refractive index, where in 2-dimensional phase imaging you can't report the refractive index. So they do have different applications. With something like typography, you have benefit of multiple cells, larger field of view, whereas hollow tomography, you are dealing with initially, before stitching, a smaller region of interest.
Okay, and from Gregorz, do we need any external standards of known refractive index to calculate the refractive index of the unknown substances inside the cells?
So the refractive index is calculated as a difference. We provide into the algorithm the refractive index of the medium, and therefore we can calculate the refractive index of the sample. But it is important to calibrate as well. So we do this with non-refractive indices of beads to run a calibration check regularly on the systems, and we are working also to have a more standardized phase target as well for three-dimensional hollow tomography. Unfortunately, unlike confocal microscopy and things like that, there's no standard. There's only few standards available. One that I know of for quantitative phase imaging.
Okay, and a couple of people, so Roland and Juliana, are interested in what's the depth limitation, the sample thickness that you can do.
So this is focused around a single cell or a couple of layers. So just to give you an idea, the 3D volume that we acquire is the maximum we acquire is 80 by 80, and in Z is 40 microns. So we are dealing with a cell or two cells. We have done some tissue imaging, but very thinly sliced tissues. Okay.
And David said, can you see the microtubule cytoskeleton? He couldn't see it in your images.
Again, this will depend on the cell type. I get asked a lot of questions of, can you see mitochondria, can you see microtubules, etc. And in most of the cells that I've seen, I've not been able to see microtubules, but in certain cells, I have seen mitochondria. So it all depends on the cell type that you use and whether you can detect these features. But I will say that it's not as clear cut as saying that these are mitochondria and they have a very non-refractive index band. In reality, they have a very similar refractive index band to other membrane-bound organelles within the cell.
Okay, right. In the interest of time, I think we'd better stop there. So if anyone wants to attend session 2, which focuses mainly on cryomicroscopy, then you need to exit this session and click on the link to session 2. And we will see you there shortly when we get that session set up. So thank you to all the speakers. That was a fantastic session, and thank you to all the attendees and all your questions. We will try and get your questions to the speakers offline, and hopefully they'll be able to get in touch with you. So thank you very much once again. We'll end this session now, and we'll see you in session 2. Okay.